Hey, fellow mathers. Welcome to the podcast where math is figureoutable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figureoutable, we are on a mission to improve math teaching.
Because we know that algorithms are amazing human achievements, but y'all, they're terrible teaching tools because mimicking step-by-step procedures actually traps students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing, building relationships with your students, and grappling with mathematical relationships.
Thanks for joining us to make math more figureoutable.
Hey.
Kimberly.
Yeah.
What's up?
In this episode, we're taking a look back at some episodes where we chatted about important topics in high school classrooms. We're tackling logarithms and a problem string you're sure to love, plus sharing when Pam got hooked on thinking about equations of lines. And we've got some discussion about one of the 3 ways to reason functionally. Here we go.
There you
Okay, here's another set of numbers. How about 5? So I'm going to just put that L in front of it again, just random. 5, comma 25 equals 2. Is there any relationship between those numbers?
Yeah.
Okay, what?
5 squared is 25.
So 5 to the second power is equal to 25. Okay, cool.
Yeah.
The next one, again, L, 3, comma 81 equals 4. Are those related in the same way?
In the same way, meaning how
the other two? Like the other ones were 2 to the third power equals 8. 5 to the second power I can read is 25, and then 3 to the is
And can I tell you how I?
Yeah, what were you thinking? You paused.
Yeah, I did, and I was like, what do I know about 81? That's 9 times 9. So that's 3 squared and 3 squared. So that would be 3 to the 4th.
Oh, nice. And I might even, as a teacher, write down exactly what you just said. 9 times 9 equals 3 squared times 3 squared equals 3 times 3 times 3 times 3.
Yeah.
Hey, sure enough, there's 4 3s.
Yeah.
And so that's like that 81. So 3 to the 4th equals 81. Okay, cool. Another one. This time, so we've kind of got this sort of set pattern. If I would look at those 3 problems, we kind of have a number, and then the power equals the exponent. Does that make sense? So like we had 2, 8, 3, and then 5, 25, 2, and then 3, 81, 4. It's all, somebody might say that's a little out of order, but the numbers are all related in a way. Okay, cool. So this time I'm going to leave one out, and I'm going to ask you to fill in the one that's left out. So I'm going to write the L down again, and then I'm just going to say 2, comma 16. So what's the equals on that one if it's following the same pattern? And how are you thinking about it?
Yeah. So again, I thought about 16 as 4 times 4.
Okay.
And so I was thinking 2 squared times 2 squared. So it would be 2, comma 16 equals 4.
2, comma 6, because 2 to the 4th equals 16.
Yeah.
Cool. So it's almost like saying 2 raised to some power is 16. What is that power? 4.
Yeah.
Maybe I should say 2 raised to some exponent. Sue is always on me about getting these terms right, and she should be. 2 raised to the exponent of 4 is equal to 16. Okay, cool. Or sorry, let me say that in the order of the numbers. 2 raised to some power, 2 raised to some exponent is 16. And that exponent that's the equals 4. Yeah. But there, I said it in the right order. Okay. Next problem. I'm going to leave one of them out again. Just one of them, random. And then you can kind of see if you can help. So this time I'm going to L 9, comma 81 equals blank.
9, comma 81 equals 2.
2, because
9 squared is 81.
Cool. So 9 to some exponent is 81. Oh, that exponent is 2. And we could actually look above where you had said 9 times 9 above.
Yeah.
To kind of connect that one. Okay, cool. Next one, again, I'm going to leave one out. L 5, comma 125 equals blank.
3.
Because
5 times 5 is 25. Times 5 is 125.
Cool. So nice. Next one, L, and I'm going to do 11, comma 11 equals blank. Is that a typo? No. I think that's what I want. Yeah, 11, comma 11.
1.
You know when I say, is that a typo? I'm kidding, right? That's a teacher move.
Most of the time. Yeah.
Most of the time it's a teacher move.
Yeah.
You said it was 1?
Yeah.
That's a little different than all the other ones. Can you say more about that? You pretty sure?
Yeah. 11. to the first power is 11. Like it's 11 times nothing else.
Any number to the first power is that number.
Yeah.
So that seems kind of helpful. Okay, cool. So mathematicians notice that there is this relationship between numbers and the exponents, and then that power, that if I do the exponent, if I multiply that base times itself, that many bases times itself, then we'll get that power. And they notice this relationship, and they call those exponential relationships. And they started to notice there were times when they wanted to solve for the exponent, exactly like you just did, where I said, well, I have 9 and 81. What's the exponent? If I have 5 and 125, what's the exponent? If I have 11 and 11, what's the exponent? And you were like, well, here's what it would be. And that was like sort of like solving an exponential equation. So like, for example, on the 5, 125, I could have written that as 5 to the x equals 125. But instead, I wrote it as 5, 125 equals x, or equals blank.
Mm-hmm.
And so it was kind of this idea that if we have exponential relationships floating around, there are times where we have the base and we have the power, that number that we've multiplied it out to get, but we don't know the exponent. We don't know the missing exponent. Mm-hmm. And somewhere in history, and I don't actually know a whole lot of the history here, but somewhere in history, somebody said, hey, let's call that a logarithm. Now that word is a logarithm, not algorithm. So those are two different things. An algorithm is a series of steps to solve any problem, any type of problem in the class of problems. A logarithm is exactly expressing this relationship that we've been talking about. So I'm going to give you another. That's why I've been using the letter L. It hasn't been random. It was kind of get you ready for. What if I were to say that right underneath the problem we just had, L, where I had 11, 11 equals 1. This time I'm going to say log. I'm just going to finish the word now. So log. Then I'm going to write 8. Then I'm going to say of 6, a little tiny 8 down below. And then I'm going to say of 64. So the 64 is kind of on the same line as log, and the 8's like a little, what do you call that? Subscript. So log base 8 of 64, or log 64 base 8 is equal to what? So the numbers are in the same places they were before. They should follow the same pattern. So I'm just going to tell you that we're still asking the question, 8 raised to what exponent gives you 64?
2.
So you're going to fill in that blank with 2. So I know this is a verbal podcast, so I'm just going to read out loud what we have down now. We have log base 8 of 64 equals 2. And why again, Kim? Can you say why again?
Because 8 times 8 is 64.
So 8 squared is 64. Nice. Okay. Yeah. So what if I just said, well, then I'm kind of curious about log base 42 of 42.
1.
That's just 1, because 42 to the first power is 42. What if I said log base 10 of 1000 equals what?
It's going to be 3.
Because?
Because I was thinking 100 times 10, and 100 is 10 times 10, and then times another 10.
So 10 cubed equals 1000. Therefore, log base 10 of 1000 equals 3. What if I said, we're almost done, log base 16. Today we're going to talk about writing the equation of a line, given some information. So if I give you a point and a slope, write the equation of a line. If I give you 2 points, write the equation of a line that contains those 2 points. I could describe the line. I could say it's vertical, and it goes through this point. Lots of different things that I could say, or really just a few sets of things that we typically say, that then we would expect a student to write the equation of a line. Okay. Uncle, right? I cry uncle. Of all the things we've talked about, this surely we have to have formulas for this, right? Surely we have to have step-by-step procedures. I mean, you can't reason about writing the equation of a line. Or can you? What would it be like to work with kids' intuition to help them reason and find strategy for writing the equation of a line? Let's do that. So let me just paint a picture. When I travel around and I look at teachers, classrooms, students all across the nation, when I've looked at kids solving writing the equation of a line, I see often a very particular thing happening. Say kids are finding the slope between 2 points, finding the rate of change between 2 points. I often see this. I see minus, minus, divide. I see kids finding the rise, the run, and then dividing, right? They're going to subtract, and then they're going to divide the rise divided by the run, rise over run. I see that a lot. And it becomes this very procedural thing to do where they sort of do that, and then they plug that into a formula, and then they do a bunch of combining like terms and messing around, and then they come up with like y equals mx plus b, or maybe the standard form ax plus b y equals c, like maybe like all that. And if you guys don't teach higher math right now, you're like all the alphabet soup, like all the stuff that's happening. I see a lot of procedures and step-by-step stuff. One day I was doing a workshop with teachers in Texas. So I live in Texas. I was doing a lot of work with teachers in Texas early in my career as I was teacher educator, a math teacher educator. And I had already figured out a few ways of helping teachers parse out how we can use intuition to solve or to write the equation of a line. But I had not developed a particular strategy that I want to work on today on the podcast yet. I hadn't developed it yet. And so I handed out some points to the teachers, and I was having them do some things. And we're going to talk actually about that strategy a little bit more next week. But they were just looking at a set of points, and they were supposed to write the equation of a line. And all of a sudden, I was circulating in the room, and we had a huge group. I do not like to do workshops this big. In fact, this might have been the last that big workshop I did, because it was put on by the state, and they forced it. And I don't know, I had like 50 people in the room, just me, 50 in a huge room. It was terrible. So I'm wandering around. I like to do 35. 35 is it's a great in person. It's not bad on Zoom. 35 is pretty good. I don't know why, but that's less than 35 can actually not be so, especially less than 20. Anyway, you don't care. So I'm doing this big group. I think it was like 75 people in the room. I'm wandering around, not wandering. I'm circulating, and I'm purposely watching what people are doing with the set of points that I'd given them. Their job is to write the equation of the line. This one gal, I wish I remembered her name. She goes, "Don't look over my shoulder." And I was like, "Oh, okay. All right. What, do you want to tell me what you're thinking about?" "No." And I was like, "Okay." She goes, "I'm not math." And then she goes into this whole like, "I'm science. I don't do math. I whatever." And all these disclaimers about why I should not be looking at her work. And I said, "Okay, but I'm actually curious. You have an equation written there. How'd you do that? Like, were you just following steps and not kind of the way we were talking about? Like, what were you doing?" And she goes, it just jumped out at me." Ooh, I got intrigued. Anytime somebody tells me that their intuition was involved, that something pinged for them, I'm interested, right? I'm thinking about that, and I'm thinking about that a lot, right, in that moment. So I'm like, hey, I'd be really curious what you were just thinking about to find the equation of the line. And she said, "Pam, I just see it." I said, "What do you just see?" And she goes, "Look at them. If you add those together, no, if you subtract them, I get 1 every time. So the equation's just x minus y equals 1. I said, "I'm sorry, what?" She goes, "I know, go walk away. I'm not math, whatever, blah, blah, blah." And I said, no. What did you just say? And she said, I had given her 4 points. And she said, if you look at all of the x values, and you, from one of the x values, you subtract its y value, every time I get 1. So I just wrote the equation x minus y equals 1. I said, "Say that again?" Y'all, it was so new to me to like look for patterns in the table of values. So she had 4 points. She looked at the x values. She looked at the y values. If given one of the x values, when she subtracted the y value, so like if she had 2 as the x value and she had 1 as the y value, she said 2 minus 1 is 1. And I was like, "Well, that's true." And she goes, "Okay, but look at one of the other values. So if it was 6 was the x value and 5 was the y value," she said, "Look, 6 minus 5 is 1. So every x minus every one of these y's gives me 1. So I just wrote the equation x minus y equals 1. To which I said, "Can you do that?" I was the sort of Z perspective growing up. I was the one who memorized all the things and did all the steps. I was hooked. I was fascinated that there might be sets of points that I could find a pattern, that I could just write down that pattern and have the equation of a line. Kim.
Yeah.
Can we work on that today a little bit?
Sure. Let's do it.
it used to be back in the day when I took high school math, we didn't even talk about transformations. And so I really applaud the fact that now we've got transformations helping us understand how we can think about parent functions and how those transformations just affect those parent functions, and we can think about the graphs of the functions as they change. However, if we're not really thinking functionally, one way we might look at transformations is we might look at a typical parent function like a quadratic function. For those of you that haven't looked at quadratic functions for a while, that's the one that looks kind of like a U. We might call it a parabola. So that parabola or that quadratic function kind of looks like a U. If I'm not thinking functionally, then I'm actually thinking of that as a static shape, like a U. Like I might think of it like a pipe cleaner that I've sort of put in the shape of a U, or even a fruit roll up or something where I've sort of got something that I can kind of put it in that shape and it sort of sits there. But a parabola or quadratic function isn't a static shape. It's actually the relationship between two variables. It has everything to do with when I go over a certain distance on a coordinate axis. When I go over that certain distance, I go up that distance squared. So if I've gone over 1, then I go up 1 because 1 squared is 1. But if I go over 2, I go up 4 because 2 squared is 4. And then I plot that point. So what that means is the further I go to the right, then I'm going to go up that number squared. That continues to happen. It's not a static U. It's really because U's kind of get vertical, right? Pretty quick. But a parabola never gets totally vertical. A parabola is always getting higher, the square, as I go over to the right, that number. But it also then is to the left. As I go over to the left, then I square that number, and the number squared is positive. And so then I go up that. And that's why we sort of get this kind of U shape, but it doesn't turn vertical in the end like a U does. It continues to grow as we go either to the right or to the left. So a first way is to understand the parent functions correctly, that they're not these static shapes that we can just sort of move around. They are, in fact, relationships between two variables. Well, then we talk about transformations on that parabola, on that shape, which isn't a static shape, right? It's a relationship between two variables. But the transformations of those is we might multiply the whole function by a number. Here's a way that you can know if you kind of have a limited functional version, if you have a limited view of functions, functional understanding, is if you think about when I do something like 2x squared or 3x squared or 5x squared, if you think about that as the parabola getting skinnier, that's a bit of a limited view. That's an incorrect, it's not a functional view of what's happening with the parabola. What's actually happening if I take a parabola like x squared and I multiply it by 3, what actually happens is as I go out, now when I go over 1, I don't go up 1 anymore. Now when I go over 1, I go up 3 times that amount. So I go over 1, I go up 3. If I go over 2 squared is 4, but that 4 times 3, that's 12. I'm going up 12. So when I go over, instead of going up the same amount I was before, I'm going up 3 times that amount. That might look skinnier if I'm thinking real static shape, but if I'm really thinking about what's happening to the points as I go further to the right, as I go further to the left, I recognize, I'm actually scaling that function by 3. Everything's 3 times as tall as it is. So the function feels very much bigger than it did before, not skinnier. Skinnier has kind of this smaller connotation, but really the y values are getting bigger 3 times as fast. That has a feel to it of much bigger. So you might notice if students are talking about transformations, especially when we're dilating transformations, we're scaling them. If they talk about that function getting skinnier when in reality it's getting bigger faster, that's a way that you can tell they're not thinking functionally. But a way you can tell they're thinking functionally if they're really thinking about how that scale factor is affecting all those y values. For example, if I take that same x squared and now I scale it by 1/2, well, that kind of, if I have kind of a limited view, I might think about it as fatter. I might look at that parabola. It's kind of it's like fatter. But in reality, it's much more like an elephant sat on it and squished it. So if you could sort of picture that kind of U shape before, now it's kind of like, why is it sort of squished? Well, because now when I go over 1, instead of going up 1, now I only go up half as much. So when I go over 1, I'll go up half. Or when I go over 2, normally I would go up 4, right? Because 2 squared is 4. But now I only go up half that much. I only go up 2. And so whereas I used to, when I would go over, I would go up a certain amount. Now every time I go over, I only go up half that amount. Wow, that's like a squashed version of the function. And so if I have this sort of sense of It got wider. That's not correct at all. In fact, it's gotten squashed. It's only going up half as much as it was before. Or say if I have x squared times 1/10. Whoa, now it's really only going up 1/10 of the way that it was every time. And so viewing transformations more as the parent functions are these infinite sets of points. And when I transform them, I really have to think about what's happening sort of point by point, and then accurately describing what's going on. So I know I'm doing this all in the air. It's really hard to do. I hope you're getting sort of a sense of what I'm talking about.
Sure. And it sounds like you can almost hear the difference between a student who's thinking functionally based on how they're describing what's happening to the parent function.
Yeah, absolutely. It's a great way of putting it. Yeah. Cool.
Okay, so we talked about slope a little bit and talked about transformations. You said there was one more thing that you want to talk about. 912 is where we wrap everything together and move into functional reasoning. And there's a lot of ground to cover, but it's so much fun when you can think and reason. Thanks for making math figureoutable instead of rote memorizable for your students, high school teachers. We know they're better for it. Keep up the great work. Thanks for tuning in today. If you found value in this episode, you'll love our books.
From our numeracy problem string series for grades kinder through 5th, to resources for middle and high school like Building Powerful Numeracy and Algebra and Advanced Algebra problem strings, we have books to support your journey towards teaching math that's figureoutable.
Visit mathisfigureoutable.com/books to browse the full collection. See you next time.
And keep making math figureoutable.